Alright, so now we can go back to looking at equilibrium problems. So in equilibrium problems, we have two conditions now. Earlier in the semester, we worked with the idea that force net equals 0, and this means that the motion in the x and y and potentially z direction does not change. So the object is not accelerating, the motion is constant, or the velocity is constant, whether it's 0 or some value that stays the same. Doesn't necessarily mean that we are at rest, but it means that when you sum your forces, you get 0. Now we're going to add our second condition where the torque net is equal to 0. So this means that the rotational motion doesn't change. So your angular velocity remains the same value, and your angular acceleration is 0. So that when you sum each individual torque acting on the object, you get 0. So we're going to use similar problem-solving steps that we did before, but we do have to diverge a little bit because torque matters not only with the force, but where that force is applied in the system. So you still need to pick a single object to sum forces and torques on. Usually it is going to be the homogeneous symmetric extended objects. We apply this a lot to things like bridges or to boards, to ladders, things that are horizontally displayed. Now, instead of drawing just a plain old free body diagram, you need to draw a diagram labeling where all the forces are applied. So you still need to write out your list of forces, but not only does it matter what direction the force is applied in, but where the force is applied on the extended homogeneous object. So you need to draw a diagram labeling the force that's applied 1 meter from one end, and the force of gravity at the center, and what forces are acting in the positive y direction and where are they acting at. So you need to draw an extended diagram that shows not only what force is applied in what direction, but where on the extended object that it is applied. Then you need to write an equation summing the torques, where you do F times R for each individual force leading to a torque. You then need to define where on your homogeneous extended object that R equals 0. And there's a little bit of a strategy for picking this, because often in these torque problems, we end up applying the concept of summing torques rather than forces, because you'll have two unknown forces, where if you went to sum forces, you would have two unknown values. And the goal is to pick R equals 0 at the value you're not trying to find, so that when you take force times R, anything times 0 is 0, and that force drops out because you multiplied it by 0. And then you only have one unknown in your problem and can solve for it. But once you define where R equals 0 is at, all of your lever arm distances are going to be relative to that position. So for example, if I have an extended object with a force applied here, if I set R equals 0 here, your R value would be this value. But if you set R equals 0 over here at the other end, your R value would be that. The other thing to remember is that where you set R equals 0 is where your sort of fake rotation point is. And that changes whether the torque is positive or negative. So if my fake rotation point is here, and this force is applied downward like I have it drawn, that's going to be let's say it's applied downward, we're rotating around this point here, that would be a clockwise rotation. Versus if we put our rotation point over here, that would actually lead to a counterclockwise rotation. So where you put your rotation point actually changes whether the torque is positive or negative. You can then, once you've determined all your lever arm distances and plugged in your force values and decide whether the torques are positive or negative based upon where you put R equals 0 at, you can then finally solve for your unknown, or if you still find that you have two unknowns, you can try summing forces and see whether that allows you to solve the problem initially.